How could anything possibly survive the crushing gravity of a black hole? It's an environment so violent it rips apart entire stars. A place where our understanding of physics gets weird. It seems like an impossible question. But the secret isn't hiding in the depths of space. Nope, it's in the deepest, most extreme part of our own planet. To understand how to survive the impossible, we need to meet the bizarre and seemingly fragile snailfish of the Mariana Trench. First off, let's get one thing straight about the cosmic horror that is a black hole. It's not really an object. It's a region of space-time where gravity is so intense, nothing, not even light, can escape. So, forget the idea of pressure like we feel it. You wouldn't be squeezed like a grape. You'd experience something far stranger, a process physicists delightfully call spaghettification. Imagine you're falling feet first toward one. The gravitational pull on your feet would be exponentially stronger than the pull on your head. This massive difference in force, called a tidal force, would stretch you vertically while squishing you horizontally. You'd be pulled into a long, thin strand of atoms, like a piece of spaghetti, long before you ever reached the center. No material we know of, especially a living body, could ever withstand that. It doesn't squeeze, it shreds. Now, physicists do talk about theoretical concepts of pressure related to black holes, but that's all wrapped up in quantum thermodynamics. It's not a physical force you could feel. The real danger is gravity gone wild. Okay, let's pull back from the edge of the cosmos and plunge into the deepest abyss on Earth, the Mariana Trench. It's a nearly 7-mile deep scar in our planet's crust, cloaked in eternal darkness and near-freezing temperatures. If you could stand at its deepest point, Challenger Deep, the column of water above you would exert a pressure of around 1,100 times that at sea level. To put that in perspective, imagine the weight of 50 jumbo jets stacked right on top of you. That's the kind of force we're talking about. It's so immense it actually compresses the water, making it about 4 to 5% denser than at the surface. Any submarine not built for this depth would be crushed into a tin can in a heartbeat. This environment should be just as hostile to life as the vacuum of space. For a long time we thought it was. Turns out we were wrong. Down here, in this crushing, desolate world, lives an animal that seems to defy all logic. It's not some monstrous leviathan with thick armor. It's small, translucent, and looks about as sturdy as a piece of jello. This is the Mariana snailfish, Pseudoliparis swirei. This little tadpole-shaped creature, with its scaleless skin and delicate frame, is perfectly adapted to this world. It's one of the deepest living fish ever discovered, comfortably navigating a world that should, by all rights, pulverize it. While it once held the top spot, other snailfish have since been found even deeper in trenches near Japan. In this seemingly barren wasteland, the snailfish is a top predator in its niche. Feeding on tiny crustaceans it sucks up from the sea floor. The question is, how? How does this ghost of the abyss stare into the face of impossible pressure and just exist? The answer lies in completely rethinking what it means to be strong. The snailfish's secret isn't to resist the pressure, but to yield to it completely. It's a masterclass in strategic surrender. First, forget what you know about a typical fish. The snailfish has no swim bladder. That gas-filled organ most fish use for buoyancy would be a fatal flaw here. The external pressure would cause it to instantly collapse. Instead, the snailfish achieves neutral buoyancy because its body is a gelatinous, water-based matrix. Its bones tell a similar story. You might expect them to be incredibly dense, but the opposite is true. The snailfish has a cartilaginous skeleton with very little ossification, meaning its bones aren't fully hardened. They are flexible and pliable. Its skull isn't even fully fused, which helps it accommodate the extreme environment. Because its body is largely made of incompressible fluid and has no air pockets to crush, the insane external pressure is perfectly matched by the pressure inside its body. It doesn't get squashed because there's nothing to squash. But the most profound secrets are at the molecular level. The snailfish's cells have high concentrations of a molecule called trimethylamine N-oxide, or TMAO. High pressure can wreck the delicate 3D shapes of proteins, the machinery of life. It does this by forcing water molecules into the tiny folds of proteins, distorting them until they stop working. TMAO acts as a kind of molecular bodyguard. It helps organize the water molecules around the proteins, essentially keeping them from invading and deforming the protein's structure. It's one of the key chemical adaptations that allow the snailfish's cells to function under forces that would shut down any other creature's biology. And here is where our story takes a sharp turn. From the deepest ocean trench right into our own bodies. Because the same molecule that allows a snailfish to survive 7 miles down is, right now, circulating in your bloodstream. But for us, its role is different. For humans, TMAO is mostly a byproduct of our diet and gut microbes. When we eat foods rich in certain compounds like choline and carnitine, found in red meat and eggs, our gut bacteria metabolize them into a gas called TMA. That TMA is absorbed, sent to the liver, and then converted into TMAO. Interestingly, when you eat fish, you're often consuming TMAO directly, as it's already present in their tissues. It's a stunning example of evolution taking one chemical and using it for wildly different purposes, a high-pressure shield in the abyss, and a complex metabolic marker in us. We've journeyed to the deepest part of our planet and uncovered the biological miracles that allow a creature to exist under forces that seem impossible. We've found the secrets in its flexible bones, its gelatinous body, and a special molecule that protects its very cells. So, let's go back to our original mind-bending question. Could the Mariana snailfish, the ultimate survivor of pressure, withstand the forces of a black hole? The answer is an unequivocal, resounding no. The reason is the physics. The snailfish is a master of surviving hydrostatic pressure. That's a uniform, compressive force, being squeezed from all directions at once. Its entire biology is built to yield and equalize that pressure. A black hole, as we learned, doesn't deal in hydrostatic pressure. It deals in tidal forces, the stretching and tearing force of spaghettification. It's a differential force that pulls harder on one end of an object than the other. The snailfish's soft, yielding body would offer zero defense. Its adaptations for being squeezed are useless against being stretched and torn apart at the molecular level. It's like designing the world's best wetsuit for the cold, only to walk into a blast furnace. The gear is brilliant, but it's for the wrong battle. The universe is filled with these incredible, mind-bending scenarios. From the crushing deep to the stretching void, the rules of survival are constantly being rewritten. If you found this journey from the bottom of the ocean to the edge of a black hole fascinating, subscribe for more explorations into the extremes of science. And let us know in the comments, what other impossible environments do you want to see us explore? The Mariana snailfish might not be a black hole survivor, but that doesn't make its existence any less miraculous. It's a profound testament to the sheer, stubborn adaptability of life. It shows us that when faced with impossible challenges, the solution doesn't always be to be stronger or more resistant. Sometimes, the key to survival is to become softer, more flexible, and to yield. The snailfish couldn't conquer the cosmos, but it did conquer the most alien world on our own planet. And in doing so, it pushes the boundaries of what we thought was biologically possible, reminding us that even in the deepest, darkest corners of our world, Wonders are still waiting.